Hello everyone. In this video we are going to learn a bit about proving things via mathematical induction. So we're actually going to start with something we've seen before here. So we've seen recursive formulas for sequences, and so I'm just going to give one here. So we have the first term is 1, and then each of the subsequent terms you take the previous term and then add 2n minus 1. So this is for n greater than or equal to 2. So first, let's just look at a few terms. What we're going to do is guess a closed formula and then actually prove it. Because thus far we've really only guessed it based off a pattern and kind of assumed it to be true. Now we're going to show that our guess actually is correct. Okay. So if we write out the first few terms, so a1, a2, let's do like 5 of them. So a1 is obviously 1. a2 then is 1 plus 2 times 2 minus 1. That's going to be 4, right? The ones cancel. A3, then take the previous term, plus 2 times 3, or 6, minus 1. It's going to be 9. A4, 9. 2 times 4, so we're at 17. Minus 1, we get 16. And then A5, finally, we get 16 plus 10 is 26, minus 1 is 25. So if you look at these, hopefully you see a pattern there. Our guess should be that an is n squared, right? We've got 1 squared, then 2 squared, 3 squared, 4 squared, 5 squared for the first, second, third, fourth, and fifth terms. Let's actually prove that this is true always, because of course we've written out 5 here, but how do I know for sure that a1000 is 1000 squared? Because I don't want to go up that high, right? So how do we know for sure? This is where mathematical induction comes in. So first I'm going to just kind of like broadly talk about what mathematical induction is. So the idea is as follows. You want to think of this as like an infinite staircase here, okay? Maybe my art is subpar, so I will label it. It is an infinite staircase. So if you want to know that you are able to climb as high as you want, right? If someone asked you to get to the 10 billionth step, you could get there. If they want to go farther, you can get farther. That you can climb as high as you want no matter how big the number is. It really boils down to two things, okay? So first, you have to be able to climb the first step. If that's not true, then, well, how are you going to get very high if you can't start, right? And the second thing you need is from any step, you can always get to the next. Or you can climb the next. So think about this. You can think of the staircase, or if it helps, dominoes as well is a good example, right? If you knock over the first domino, and if one domino falls, the following one falls, then all of them will fall, right? And so the idea here is, okay, I climbed my first step, and then this second thing says, okay, I climbed one. From this first step, I can climb to the next step, right? From the second step, I can climb to the third step. Third to the fourth, fourth to the fifth, and so on. And you can keep going forever, right? From the 10 billionth to the 10 billion and first. So this is enough to prove something. And so the idea here, so now I'll make this a little bit more formal. So let P be a proposition. And we'll think of this as having steps. So basically you want like P of 1 to be true, or basically the first step in your thing. And then if P of some number is true, your nth step, then so is P of n plus 1, okay? And so I can just label that here, right? This is step 1, and then later, right, if you have step n and step n plus 1, the idea is you can always climb that step. All right, so let's actually use this in the example to see how it actually works out. All right, so we have our recursive formula for this sequence, and our goal is to show that an is n squared for all n greater than or equal to 1. So this is going to be our P of n proposition, okay? So it's the statement that an is n squared, okay? And of course, it takes in an input, right? This is a predicate, and so it becomes a proposition the second I plug in an actual value there, all right? So how do we prove this? Well, we're going to use induction. So what was my first step? I want to show that P of 1 is true. So what does that mean here? Well, that means that A1 is 1 squared. Right, so I'll say i.e. A1 is 1 squared. Well, this is obviously true, right? Because we're given A1, it's 1. And 1 is 1 squared. So we're good. P1 is true. Now the second part is to show that P of n implies P of n plus 1. So again, we want to translate this. What does this really mean? This means that if an is n squared, then an plus 1 is n plus 1 squared. Right? That's P of n, and this is P of n plus 1. We want P of n to imply P of n plus 1. So here is where we're going to actually use that recursive formula. Okay, so we get to assume P of n is true. So assume an is n squared. Okay, then what do we know about an plus 1? Well, we know from the recursive formula that it depends on an, right? So it's an plus 2 times n plus 1 minus 1 from the recursive formula. But I know what an is. By my assumption, I can fill this in as n squared. And then I can just kind of do some algebra here, right? If I distribute plus 2n plus 2 minus 1, and then this becomes n squared plus 2n plus 1. And I can factor this, right? This is n plus 1 times n plus 1, or n plus 1 squared. And so this is exactly what we wanted, right? This is that P of n plus 1 is true. An plus 1 is equal to n plus 1 squared. And so this actually is the entire proof. So basically what you could say to maybe close it out if you felt the need is by mathematical induction, right? An is equal to n squared for all n greater than or equal to 1. So again, the idea is start at the first step, show that's true, and then from any step, so assume it's true at a certain point, show it's true on the next step. And that's exactly what we did here. Okay, so now for your exercise, it's going to be something similar just to get the hang of this, and we'll practice more in class. So let an be this recursively defined sequence. And I'm just going to go ahead and tell you, you can verify via some examples that this seems correct, but the closed form is 4n minus 2. And I want you to prove that by induction. So I'm just kind of breaking it down to steps here. So first, write down what this P of n is, what the nth statement is that you would be proving. Show that P of 1 is true, right? Your base case is what we call this. And then show the inductive step. Show that if you're at one step, then you can always get to the next. All right. Thank you for watching.